Hello, this is Project Shark Shield, which is preventing oil spills with anti-corrosion microtextures.
So this is our team. I'm Ryan Nagel. I'm in charge of time management and scheduling for the team. I'm a civil engineering major from Boston, Massachusetts originally, and I love the ocean and ocean activities.
My name is Angel Ko. I handled the visuals and formatting, as well as a little bit of research. I'm a geosciences major with the concentration in environmental science, previously an environmental engineering major, and I am from Hawaii.
I'm Daniel. I worked on some of the design research and the graphics. I'm from Plano. I'm a computer engineering major, and I enjoy all things computer related, whether it's programming, electronics, you name it.
So, in order to give a bit of a context about our project, we're mainly dealing with oil spills. And oil spills are such a big problem because they not only affect the marine environment that the oil spill occurs, but it also affects the human communities and the industries in that area. The issue that our project aims to solve is oil spill prevention specifically. And that actually helps solve our problem a lot because it prevents them from happening in the first place. And the problem that we're addressing is to establish an effective, safe, and eco-friendly solution that is needed to prevent those oil spills from happening. Our goal for the project is to create a bio-inspired solution that effectively helps prevent oil spills in the ocean caused by the corrosion of equipment. This is our problem tree that we use to determine exactly what problem we wanted to address in our project. So in order to understand our project a little bit better, we went ahead and wanted to define some key terms that we were going to be going over later in the project, just to clear up any confusion. First of all, we have salinity, which is a measure of how much salt is dissolved in water, and it's relevant to the project because that salinity that's present in the ocean can accelerate the process of corrosion in the API metals and other materials used in oil infrastructure. Um, Second off, we have corrosion, which is the process of metal degrading, which I mentioned earlier with salinity, and it can happen due to the chemical reaction with its surroundings, namely salinity, which I mentioned before. And it's relevant to our project because that corrosion can cause oil spills, which is the problem that we are addressing in this project. Third, we have microtextures. Microtextures are microscopic patterns engraved in the structure of materials, which is relevant to the project because they can be found in various marine animals. In this case, we are going to be going over shark skin, which you'll see later in the presentation, and that can actually help prevent corrosion. Lastly, we have fouling, which is the growth or accumulation of unwanted materials on solid surfaces. In the scope of our project, that fouling occurs in the ocean through biofouling, which is the accumulation of biological material. So some previous solutions that deal with solving our problem that we are trying to address have to do with two categories. One, how the way that response is handled in regards to oil spills, and the way that we prevent them from happening in the first place. And we're going to go ahead and go over those mechanisms and why some of them might not be as effective as our solution.
All right. So starting with the response solutions. So one of the previous solutions to cleaning up oil spills in a manner of response is using booms and skimmers. And essentially, what a boom is it's a flotation device that floats on the surface of the water and acts as sort of a physical barrier to contain crude oil at the surface of the water. And the skimmer is kind of like a machine that is then used to pick up the crude oil that is contained within the bounds sectioned off by the booms. The problem with using a boom and skimmer is they can be ineffective under certain weather conditions, mainly rough weather conditions or rough sea conditions, as large enough waves can carry the crude oil up over the edges of the booms, and then essentially you have a boom that's doing nothing, that's not containing anything. One of the other solutions in terms of response is the use of dispersants. And dispersants are essentially chemicals that are used to break up material, in this case, crude oil, and it makes it a lot easier to clean up said crude oil. The big disadvantage with this one, though, is some of these chemicals that are used as dispersants can be toxic and harmful to sea life. And then another solution that goes hand in hand with that really is sorbents. And essentially, what sorbents are materials or chemicals that are then used to retrieve the oil that's been broken up or just spilled um, through methods of either adsorption or absorption. And the big issue with this one is that sorbents are prone to sinking in the water uh, as the oil is being absorbed. In cases where that's where absorption is used, um, the sorbents can become too heavy to sink. Essentially, is what's wrong. Now, those are the responsive solutions. Here are some previous preventative solutions, which, of course, our solution is more for preventative solution. But some other preventative solutions include the use of ILI smart pig devices. And what an ILI or inline inspection smart pig device is it's a sort of diagnostic device that's deployed into the pipelines of these oil pipes, and it's used to seek out anomalies from within the pipes using various methods. And we've looked at 3 individual ILI smart pig techniques or types of devices that have been used in the past, and I'll tell you why those may not really be so great in comparison to our solution in just a second. But to go over them, we have electromagnetic acoustic transducer, sorry, or we'll call them EMATs. And what those do is within the pipes, they send out ultrasonic waves that are created in the pipe's material and disperses out and looks for anomalies. If there's an anomaly that's detected by the ultrasonic waves, uh, the device picks it up and essentially notifies where appropriate so maintenance can be done. Remote field eddy currents or RFECs. Those are going to use electromagnetic fields instead of ultrasonic waves to penetrate the material again from the inside and essentially detect anomalies in the same way. And lastly, we have the mechanical contact devices or MCs, which is kind of like a mechanical arm that makes physical contact with the interior of the wall and gives notifications of issues from the inside that could jeopardize the structure of the pipe. So now the disadvantages with each of these. EMAT, the problem with that is you need to have a constant distance from the pipe's inner wall. Otherwise, you get a bad reading. And essentially, if there's too much noise going on around the device, that can disrupt readings. The problem with RFEC, on the other hand, is it can only be used in pipes that have conductive material. And essentially, it needs to have a pipe that's large enough for it to be able to fit into. So there's a size constraint as well as material constraint for what pipes that could be used in. And lastly, we have the MC devices, which all exhibit different behaviors under different circumstances. So there's a lack of consistency really with using the MC ILI smart devices.
So, when thinking of solutions related to biological functions, we asked ourselves a couple of questions. We asked ourselves, how does nature resist degradation? How does nature counteract corrosion? How does nature prevent biofouling? And how does nature reduce fluid drag? So, we thought of 3 biological models that answered these questions and ultimately helped create a solution to our problem. So the first is the shark skin structure. So specifically how the outer shape of the dermal denticles affect drag and friction between water and the surface. The second was the shark skin material, and specifically how that material provides strength and rigidity to the system. And the third and final one was mucus and its anti-biofouling properties. So that first one, shark skin reduces fluid drag by physically reducing the amount of time that particles come into contact with the surface. Additionally, this microtexture, it creates a lower velocity gradient, which essentially means that the water doesn't change velocity as abruptly when it comes into contact with the surface, which reduces friction. In a useful study we found showed that angling that protruding material, the dermal denticles, 90 degrees from the surface seems to optimize that drag reduction. And as for the shark skin material, it has separate properties that give it a strong compressive strength due to its composition of enamel and dentine. And the last model we looked at was mucus secretion. So many organisms, including certain species of fish and eels, secrete a mucus that serves as a boundary between their skin and the water. And it helps prevent parasites and other organisms that could attach to their body. And so in the manufacturing area of things, the equivalent is kind of a fouling release coating, which serves the same purpose but for pipes in our case. So after looking at all of those, we've decided that the shark skin model would be the most suitable choice for a couple of reasons. So overall, it seems to be a good balance between performance and complexity. So it's highly effective at reducing friction from water against pipes, and at the same time, it doesn't contain a bunch of complex or moving parts that would likely require maintenance and extra money down the road, unlike some other designs. Additionally, and importantly, this poses no threat to the surrounding environment or organisms or anything like that. And additionally, the high compressive strength is going to be an added benefit, as these pipes, many of them likely would be very deep underwater where there's a lot of water pressure.
All right, so now getting into the details of how. So as far as materials go, we decided on using ABS polymer plastic as the molding for which we're going to put the microtexture on and surround the pipes with. We chose this because the ABS is relatively inexpensive in comparison to other options that we looked at, and it offers good resistance to corrosion from salinity. Salinity obviously being the biggest problem to causing corrosion on a lot of these pipes in the ocean. As far as the placement goes, where we're going to be placing the molding, it's going to be in any area where pipes have the most contact with ocean water. So, for example, anywhere where pipes are completely submerged underwater is where we're going to be implementing this molding. And we also need to take into account with that the varying sizes of different pipes, radiuses of inner walls, outer walls, etc., different specifications. When it comes to production, we decided that it would be best to use a industrial 3D printing facility, because obviously the 3D printing is going to be necessary to get the intricacy of the tiny microscopic microtextures, and to be able to print that with quality. And the thing with that, though, is there could be additional costs incurred when it comes to transportation of materials, resources, and machinery from the areas where they're being sourced. And finally, as far as the attachment goes, the way we're going to be attaching this molding onto these pipes is we're going to use hydrophobic adhesive to mold the ABS around the pipes. So here's one of our early designs. Essentially, what we knew was we wanted to do something with microtexture, and we realized that the structure of shark skin denticles works really well for reducing drag, as mentioned before. So we decided, again, let's make a mold. Let's kind of use microtexture inspired by shark skin, the structure of shark skin denticles, and we'll use that molding as coating around these pipes to prevent corrosion.
Yeah, and this is our final, slightly more detailed model of our final product. And so it would be 3D printed because it's a very effective way to produce ABS plastic parts. And as mentioned before, The texture will be, printed with the protrusions at a 90-degree angle because we found that to be the most effective previously. And these printed sections, like mentioned before, will be adhered to the pipes with a polyurethane adhesive because of its effectiveness and strength underwater.
So in terms of evaluation, we did determine that our design did in fact solve the challenge of corrosion causing oil spills in the marine environments. We determined that because the materials are relatively easy to obtain, as ABS is used in many manufacturing processes, and hypothetically because we couldn't really test this in real life, placing the anti-corrosive protection on high water contact areas, such as the pipes and the holes, will prevent equipment wear in oil infrastructure, effectively preventing oil spills. Some of the problems that we came across in our design were the choice of molding material, because it's pretty hard to find a material that's resistant to salinity. Even the industry standards that are used in oil infrastructure equipment, such as the API metals, are even susceptible to salinity and the durability that's required for that underwater pressure, as well as being inexpensive. Another problem we had was deciding on the pattern of the microstructure, as mentioned previously a couple times, the shape of the denticle protrusions, which since we aren't able to test them in real life, we weren't able to come up with the best shape to make this product the most effective. The most obvious problem that we had with this was cost, as well as estimating that cost. Since it's really hard to find current models that use these microscopic denticles, because currently the real life examples that we have so far are medical applications where these are used in medical catheters to prevent bioadhesion, to prevent infection in patients. That's obviously on a really, really tiny scale, whereas with our product, we would need it to be on the scale of covering an entire oil tanker hull or encasing pipes for oil infrastructure. And even without knowing the exact cost, we know that there will be a major issue because the facilities needed to print will need to be at a small scale. Like, we are talking something that you can't even see with the naked eye, which is obviously going to be difficult and take a lot of resources monetarily. And in order to solve these problems in the future, we can conduct more research on printing facilities, as well as running tests on different materials, angles of protrusion, etc., to determine which is the most anti-corrosive. So we asked ourselves, is it possible to develop the product with the available technology? And we believe yes, because with the modern technology we have, large-scale 3D printing is pretty feasible, and it's actually used in a lot of industry standards, and it shouldn't be too hard to produce in the real world. Our target market is the engineering construction firms that deal with these oil rigs and oil tankers and oil infrastructure, who do work on these pipelines, as well as the energy and petroleum companies that operate them. We will sell our product by taking detailed orders of necessary pipe specifications and tolerances, because that can obviously have some variability in dimensions and even the tolerances that are required depending on where on the coastline these oil tankers are going to need to be transported, or where these oil rigs are going to be located. And we need to take that into account to ship the material in bulk. If given the opportunity, in regards to future revisions, we would potentially change the angle of the ABS denticles, as mentioned before, because we need to do more research to provide a consistent result of reduced fluid drag, which would in turn reduce corrosion, which is the objective of our project. We would also continue to reevaluate the materials used for molding to search for better options. Again, since we weren't able to research, we don't actually know how well ABS would hold in this situation. Lastly, we would possibly combine different biological models. As we mentioned before, we would possibly combine the FRC, as we mentioned, with that biological model with mucus, as well as the microstructures, which might help optimize that anti-corrosive property.
All right, so now looking at the sustainability and ethics and the impact that the project will have. So as far as environmental impact goes, there are going to be pollutants released. There's going to be carbon emissions. However, the good news is most of that will just be due to transportation of materials, construction, and initial construction and maintenance that's done over time. you need transportation vehicles to get materials and machinery to and from the job site. In some cases, to get workers to and from. Obviously, machinery that's going to be used for construction is going to need fuel, and then there's also going to be some waste created in the process of 3D printing at the 3D printing facility. Looking at specifically the energy, there's going to be fuel that's going to be necessary for vehicles, workers, equipment, resources, and we're going to need electricity for operating batteries and operating lighting. There's going to be times where lighting is going to be necessary to see what we're doing first for whoever's working on the projects to see what they're doing underwater. There are opportunities for conservation, though. That's the good news. And to do this, it would be best to conduct construction and maintenance during the day to take advantage of natural light rather than having to spend money on powering artificial light, and also sourcing locally where possible and feasible. Because if you're sourcing locally, that's a lot less transportation distance and a lot less fuel and fuel cost for moving materials and machinery around. And again, there can always be improvements on protocols for waste management. So continuing with the sustainability, like I said before, materials can be sourced online, but it makes more sense to source them locally at fair market prices. And there's additional research that can always be done regarding labor policies to make improvements on that, but that kind of goes with what we already talked about in the last slide. There is going to be a generally low impact on the public. The good news with that is, so long as these pipelines that have work and maintenance and construction being done on them are away from populated areas, it's not going to impact anyone. There might be increased water traffic if it's in an area where water traffic does occur. So that's really the most as far as societal impact goes. But with regard to businesses, unfortunately, there are going to be some inconveniences in certain areas. I mean, it all depends on context. But areas where businesses might run like scuba diving expeditions and stuff like that, or any sort of water activities within the proximity of construction, those will be affected. But importantly, aside from that, there's going to be a low negative impact on the environment. That's why we chose the materials we did. They won't break as easily. They won't leave. There won't be a whole lot left behind. There's a lot of recyclability that could be taken into account. And these sections of these pipes can be removed, taken to scrap yards, and be repurposed for something else.
So as for the future, we believe this coding can be applied to other areas, including dams, fishing boats, and more. As for things we think we could revisit, well, we think the very specific details of the dermal denticles and their angles, which I know we keep mentioning, but it's essentially the heart of our system that we designed here. I think if we could get a slightly better grasp on how exactly the drag and velocity gradient are affected by those, that could benefit us in the future. So why do we believe that this design is bio-inspired? So overall, it's effective, but at the same time, it's not overly complicated, which generally follows the principle of nature and its evolutionary design. And of course, we kind of have those characteristics as a result of closely modeling something that is of nature's own design, which in this case is shark skin. And this design would be classified as a system because it contains components that interact with the surroundings. And it does kind of have a form, but our design is more focused on the larger effect of the form on the system. So that's why we consider it a system. So yeah, here are our references used in our research. And yeah, we appreciate your time. Thank you.
Yay.